Hi, welcome back to A Slice of Physics. We're going to continue our discussion on circular motion by looking at an example that involves centripetal force. The specific example we're going to take is a car that's negotiating a curve on a freeway, and we want to see how a charm that's hanging from the rear view mirror responds to this motion. So our question says that a car is driven on cruise control at 56 miles per hour. As I read this, I'm noting that the speed's not given in SI units, so it might require a conversion. It's being driven on a freeway as the freeway curves to the left. The circular curve has a radius of 90 meters, so that's in SI units. What is the angle with respect to the vertical of a string supporting a rear view mirror charm? And how does the tension in the string compare to the charm's weight? So as you read this, it seems like there's a lot of words and not enough numbers, so you're wondering if you can even solve this. But once again, when you're in those situations, I want you to just follow these steps, and it'll lead you in the direction you need to go. So for all free body diagram and force problems, the solution steps or the slice of physics recipe I gave you is outlined here. So let's start with the first step. And in this case, I'm going to draw two pictures. So here's the car, and I'm now viewing it from the sky. So I'm seeing the car from the top. So here it is, headlights over here. And it's negotiating a curve or a turn. And the circular curve has a radius of 90 meters to the center somewhere off this picture. And the speed of the car is given as 56 miles per hour. It's in cruise control, so that speed's not changing. And I need to convert this to meters per second, so I'm going to go ahead and make that conversion right now. I've got 1 mile over here, 1609 meters. 1 hour over here, 3,600 seconds. And when you solve for that, the miles cancel, the hour cancels, and you'll get 25 meters per second. Okay, so that's what's happening with the car. Now let's see what's happening with the ornament. And for that, I'm going to go inside the car and draw a picture of what I see if I'm sitting, let's say in the rear seat at the center. I'm going to take a zoomed in view of the rear view mirror. So here's my rear view mirror. And because the car is turning to the left, you know that the charm is going to swing to the right. So let me draw that like this. Here's the charm, here's the string. And what we're being asked for is the angle of the string from the verticals. So that's the angle we're being asked for. So I'm going to show that as theta. Now, because the car is being driven on cruise control, there is no linear acceleration, but because its direction is changing, it's got a centripetal acceleration that points towards the center. So this car is accelerating to the left like that. There's a net acceleration in that direction. The charm swings away from the acceleration because remember we talked about in a previous video where the apparent force that anything feels is opposite the direction of acceleration. When you slam on, if you're at rest in a car and you slam on the gas pedal, the acceleration of the car is in the forward direction, but you get pushed into your seat. And that's simply your inertia trying to resist the change. So that's my setup of the question. I know what's going on, and I know what I'm being asked for. I may still not know how to get there from here, but once again, let's trust our steps and follow them. So the next thing is to draw a free body diagram of our object of interest. Let me do that over here. Here's my ornament. And as I draw a circle here and go around it, the only contact force is tension from the string. And tension acts right along the string as a pulling force. So here's my tension. And since that's the only contact force, the only other force I have is a long-range force of weight that acts straight down as usual. So I'll show that over here. And here's my vertical on the free body diagram. And if I draw a vertical here on the picture of the charm as well, this angle over here is also theta. That's how parallel lines work. So this is theta over here that I'm trying to find out. And I'm also going to show right next to the free body diagram the fact that the net acceleration in this case is directly to the left. And let's call that A, and that actually is v squared over r because it's centripetal acceleration, which is always v squared over r. So the reason the ornament follows the car and also makes the turn is because of this tension in the string. And you can see right away that this tension has two components. It's got a vertical component pointing up that has to balance the weight because there is no net acceleration in the vertical sense. And there's a horizontal component which points to the left, and that is the centripetal force that corresponds to this centripetal acceleration. So I'm going to label these Ty and Tx because my coordinate axes, as usual, are horizontal for x and vertical for y. Okay, so looking at my steps, I got my free body diagram, I've got my coordinate axes, and I've noted what I need to split along the x and y axis. Ty is t times cosine theta because it's adjacent to the angle, and t is the hypotenuse, and tx is t times sine of theta because it's the opposite. I can redraw tx over here, and that's opposite to the angle theta. Okay, now I'm ready to set up my equations, the last step. So along the x-axis, I have sum of forces in the x-axis equals mass times acceleration in the x-axis. And the only force I have along the x-axis is tx, and that's pointing to the negative x-axis. So I'm going to mark that as minus t times sine theta. That's what tx was. And that equals the mass of the ornament, or the charm, times the acceleration. And we know that that's also negative v squared over r because it points to the left. So I can put a minus here, v squared over r. And our goal is to find this angle theta. I could do that if I knew everything else over here, but I don't know the tension and I don't know the mass of the charm. They didn't give us that either. So I'm kind of at a loss as to how to figure this out yet. So I'm going to continue with my steps. I'm going to go to my y-axis and say sum of forces in the y-axis equals mass times acceleration in the along the y-axis. And in this case, the acceleration along the y-axis is 0. So the sum of forces in the y-axis is an equilibrium condition where they need to add up to 0. So here I would have plus t times cosine theta because ty is in the positive direction and ty was t times cosine theta minus the weight, and I'm going to write that as mg equals 0. So now I've got another equation with all of these variables, but I still don't know t, theta, and mg. So it looks like I got 3 unknowns and only 2 equations. So I may be confused as to how I get there, but let me get the value of t here in terms of the other variables and substitute that over here and see what happens. So from this y-axis equation, I can solve for t as mg over cosine theta by adding mg to both sides and then dividing by cosine theta. And I can plug that into the first equation. So I'm going to move over here and do that. And by the way, the minus on both sides will cancel each other. So I can just have positives on both sides. And rather than t over here, I'm going to put in this value. So I've got mg divided by cosine theta. That's all that is for t. And there's a times sine theta over here, so I'm going to retain that. And that on the right hand side equals mv squared over r. Now you can see that there's a common factor of m on both sides. So if I divide both sides by m, those m's will cancel. And so now I got only one unknown here, which is theta. I know v, that's over here. I know r, that's over here. So now I've made good progress and I can find this. Sine theta over cosine theta is simply tangent theta, and I've got a g over here on the left hand side, which when it moves over to the right hand side, that side would become v squared over rg, which is 25 squared, speed in meters per second, divided by 9 meters of radius times 9.8 meters per second squared of acceleration due to gravity. You can verify for yourself that all the units will cancel each other. So theta would simply be tangent inverse of all of that, which is 0.709, and that gives me 35.3 degrees, or down to 2 significant digits, simply 35 degrees. So we've solved the first question. We know the angle at which the string slants to the right as the car accelerates to the left as it goes around that curve. Okay, so the last question was, how does the tension in the string compare to the charm's weight? I've got an equation here that's got those two variables, so let's go back to that. This one simply says tension equals weight over cosine theta. And now that I know theta, I can figure out tension as weight divided by cosine of 35.3 degrees, which gives me 1.23 times W, or I can say T is 1.2 W down to 2 significant digits. So this tells me that the tension in the string is 20% more than the weight. So in this example, we worked with centripetal force and figured out the dynamics inside a car as it negotiates a curve on a freeway.